In the dead of night on Christmas Eve 2024, NASA's Parker Solar Probe hurtled through the Sun's outer atmosphere at a staggering 430,000 miles per hour. It skimmed just 3.8 million miles above the solar surface, closer than any human-made object in history. This was no ordinary flyby. The spacecraft plunged into the corona, the searing realm where temperatures soar beyond 1,000,000 degrees Fahrenheit, while humanity held its breath for confirmation of survival. A beacon tone finally reached Earth late on December 26th, confirming the probe had survived the inferno intact. Traveling faster than any machine before it, Parker shattered its own records in speed and proximity. This moment marked humanity's first true venture into a star's atmosphere, rewriting the boundaries of exploration and daring us to confront the sun's most violent secrets. Yet this triumph was decades in the making, built on audacious vision and relentless engineering. As data begins to flow, scientists stand on the threshold of unlocking mysteries that have haunted heliophysics since the space age began. The probe's survival signals not just success, but the dawn of a new era in understanding our star. At peak velocity, Parker reached 430,000 miles per hour during its record perihelion, equivalent to circling Earth over 10 times in a single minute. This blistering speed, aided by gravitational precision, allowed it to dive deeper into the corona than ever imagined. The probe's instruments captured data in an environment where conventional spacecraft would vaporize instantly. Previous records fell one by one. Earlier passes already made it the fastest human artifact, but this Christmas encounter pushed boundaries further. Out of contact during the critical moments due to solar interference, the mission team waited in agonizing silence until that life-affirming signal arrived, proving the spacecraft's extraordinary resilience. These feats are not mere spectacles. They enable unprecedented measurements of magnetic fields, particles, and energy flows right where space weather originates. Parker's journey exposes the raw power of our star, forcing a reevaluation of everything we thought we knew about solar dynamics. For decades, the corona has defied physics. While the sun's visible surface, the photosphere, simmers at around 10,000 degrees Fahrenheit, the outer atmosphere blazes at over 1,000,000 degrees. This inversion, known as the coronal heating problem, challenges our fundamental models of stellar behavior and energy transfer. Parker dives directly into this enigma, sampling the chaotic magnetic fields and plasma where heating mechanisms unfold. Switchbacks, zigzag magnetic structures, and energetic particle accelerations offer clues. The probe's close encounters reveal how energy cascades through the corona in ways invisible from afar. Understanding this paradox is vital. The corona drives the solar wind that shapes our solar system. Parker's data promises to resolve long-standing questions, illuminating processes that influence stars galaxy-wide and our own technological vulnerability. Solar outbursts can trigger geomagnetic storms, disrupting power grids, satellites, and communications. Parker's intimate views trace how coronal mass ejections and solar wind originate, offering predictive power against these invisible threats that can cascade into technological disasters on our interconnected world. By flying through the very birthplace of space weather, the probe measures particle acceleration to near-light speeds and magnetic field dynamics. This knowledge protects astronauts, refines forecasting models, and safeguards the infrastructure modern civilization depends upon daily. The mission transforms abstract science into practical defense. As we venture deeper into space, Parker's revelations become our shield against the sun's fury, bridging the gap between stellar physics and human survival. In 1958, physicist Eugene Parker proposed the existence of solar wind against skepticism. His groundbreaking theories described a continuous stream of charged particles escaping the sun decades later. NASA honored him by naming the probe after this pioneer, fulfilling a vision long deemed nearly impossible. Parker's ideas revolutionized solar physics, explaining phenomena from comet tails to auroras. The spacecraft carrying his name now validates and expands those predictions from within the corona itself, closing the loop on a lifetime of scientific courage. This naming symbolizes the bridge between theory and daring exploration. What began as controversial equations now manifests as hardware braving the sun, proving that bold ideas can literally touch the stars. On August 12, 2018, Parker Solar Probe launched from Cape Canaveral atop a Delta IV Heavy rocket. Engineered for extreme environments, the car-sized spacecraft embarked on a 7-year odyssey. Its path required meticulous planning to survive the sun's wrath while gathering revolutionary data. Early orbits tested systems as the probe began its inward spiral. Instruments designed to withstand hellish conditions powered up, sending back initial readings that hinted at the complexities awaiting deeper in the corona. The mission's success hinged on flawless execution from day one. From launch to its record-breaking 2024 pass, Parker has completed dozens of orbits. Each one brought it closer, building toward the ultimate goal of touching the sun and demystifying its atmosphere. 7 precise Venus flybys acted as gravitational slingshots, reshaping Parker's orbit for ever closer solar encounters. The final assist on November 6, 2024, perfected its path, enabling the record 3.8 million mile perihelion without excessive fuel demands. These celestial dances not only adjusted trajectory but yielded bonus science. Images of Venus' dust ring, radio emissions from its atmosphere. Venus served as both navigator and secondary laboratory in this intricate solar ballet. Masterful orbital mechanics turned theoretical possibility into engineering reality. The gravity ballet set the stage for Parker's deepest dives, proving human ingenuity in harnessing planetary forces. Protecting the probe is a 4.5-inch thick carbon composite heat shield, 8 feet wide, with a lightweight carbon foam core, designed to endure 2,500 degrees Fahrenheit on the front while keeping instruments at room temperature. It is the unsung hero enabling survival in the corona. In the low-density corona, the shield reaches about 1,800 degrees Fahrenheit. Every sensor, computer, and system hides behind this barrier. Without it, the mission would be impossible, as conventional materials would fail within moments of solar exposure. Engineers at APL poured decades of innovation into this shield. It represents the pinnacle of materials science, turning vulnerability into strength for humanity's boldest solar quest. For instrument suites aboard Parker measure magnetic fields, plasma, energetic particles, and imaging. WISPR captures stunning visuals of the corona and solar wind in unprecedented detail during close passes. These tools operate in extremes, sampling switchbacks, coronal streamers, and CME collisions. Data streams reveal the sun's magnetic secrets and particle behaviors impossible to observe from Earth or distant orbits. The synergy of these instruments transforms raw exposure into profound insight, painting a dynamic picture of the corona's inner workings. In April 2021, Parker became the first spacecraft to enter the sun's corona. It crossed the Alphane critical surface around 8 million miles from the surface, sampling the magnetically dominated atmosphere directly for the first time. Discoveries included wrinkled coronal boundaries with spikes and valleys, plus the photospheric origins of switchbacks. These findings upended models and confirmed the probe's ability to revolutionize solar science. Subsequent passes increased time in the corona, building a richer dataset. Each encounter refined our map of the sun's outer layers. Radiation, heat, and dust posed lethal risks. Redundant systems, autonomous operations during communication blackouts, and rigorous testing ensured reliability. The mission pushed materials and computing to their absolute limits. Challenges like CME encounters and Venus observations tested adaptability. Teams iterated designs over years, turning potential failure points into strengths through innovation and foresight. These triumphs of engineering enabled the 2024 record pass, proving that human ingenuity can conquer even a star's fury. During the December 2024 pass, Parker immersed itself in the corona's dynamic plasma. It witnessed CME pileups, heliospheric current sheet crossings, and the birthplace of solar wind streams in high resolution. Switchbacks and magnetic funnels revealed mechanisms powering fast and slow solar winds. The probe's vantage exposed how energy and particles escape the sun's gravity in real time. These observations peel back layers of mystery, showing a far more turbulent and structured corona than previously modeled. Post-flyby data confirms 2 types of slow solar wind with distinct origins: alphenic and non-alphenic streams, helmet streamers, and coronal holes come into sharper focus through Parker's unprecedented proximity. CME mergers observed in detail show trajectory changes and particle acceleration risks. Whisper imagery captures these events piling up, enhancing space weather models. Each revelation builds toward solving the coronal heating puzzle and solar wind acceleration. Upcoming passes in 2025 will yield even richer datasets. Scientists anticipate breakthroughs in slow solar wind origins and deeper insights into magnetic reconnection and particle energization. These findings ripple across astrophysics, informing exoplanet habitability and stellar evolution studies far beyond our system. Parker's legacy elevates humanity's cosmic perspective. The mission exemplifies how targeted exploration yields transformative knowledge, inspiring future probes to other stars. As Parker's primary mission nears completion, its data archive will fuel research for generations. It has touched the sun, survived the impossible, and returned knowledge that protects Earth and expands our understanding of the universe. Named for a visionary, built by heroes, and flown into legend, Parker stands as a monument to curiosity. Its journey reminds us that the most extreme environments yield the greatest revelations about our place in the cosmos. The sun's secrets are yielding to science. Parker's triumph lights the way for bolder explorations, ensuring humanity's enduring quest to comprehend the universe's fiery heart.